Welcome everyone. For today's prep, we're going to look at another example for finding the area in between two curves. And for this one, we're going to see how to find the area for a region that's, well, bounded by the two curves. So it's essentially bounded between two intersection points. We're going from one intersection point to another one. And that's what we see on our graph here. So if we're looking at the graph, we got, well, two functions, y equal to x squared plus 2x plus 3, and then a second function, y equal to 2x plus 4. And if we're looking at their graphs, it looks like they have two intersection points. All right, and we want to find the area for that region that goes in between those intersection points. So we want to find that, that section bounded by the two graphs. All right, so how are we going to do this? Well, the first step is we got to figure out where do those intersection points actually occur. Well, we can kind of tell by the graph, but we want to be precise. So let's actually figure out the x values for where these two intersection points are happening. So how do we do this? Well, we take the one function and we set it equal to the other function, and then we solve for x. So what do we get here? Well, the equation is going to be x squared plus 2x plus 3 equal to 2x plus 4. So we just set our two functions equal. And now we have this equation, and we want to solve it for x. So normally the way we solve an equation is we just try to get all the terms over to one side and get 0 on one of the sides of our equation. So in this case, let's we already got a positive x squared here. So let's leave all these terms here. And let's move all this stuff over. So we'll move all this stuff over with subtraction. So I'll take the 2x, subtract it, and actually the 2x's are going to cancel. And then I'll take the 4, subtract it. So when we do that, we end up with the simplified equation of x squared minus 1 equal to 0. And then we just want to solve this simplified version. So factoring would work. Quadratic formula would work here. But I think even easier is just to try to directly solve this one. So let's actually do a direct solve. So we're basically just going to try to unravel all the arithmetic here to get x completely by itself. So directly solving for x doesn't always work. Normally factoring or quadratic are kind of the way to go, especially when we have polynomials. But in this case, there's not too many x terms, so we can actually directly solve here. So I would add 1 to both sides. And then we got to get rid of that square function, and the way we do that is with the square root. So I would rewrite this as x squared equal to 1, and then applying the square root is going to give me x equal to square root 1. And whenever we apply the square root, if the square root's not already there, whenever we apply it and we're solving an equation, we got to remember the plus minus. So we end up with two values for our intersection points, x equals 1 and x equals negative 1. And that matches up with what we see in our graph. So if we're looking at the graph here, we do see that this intersection point here happens at negative 1, and then our other intersection point, follow it down, is happening at x equals plus 1. All right, so but we actually confirmed that with the algebra. All right, so once we get those intersection points, then we want to figure out which is our top function in order for us to set up our integral. Because if we remember, when we're trying to find the area, it's the integral of the top function minus the bottom function. So we got to figure out which function's on top. Now we have the graph here. So we can use the graph. And for our purposes, we're looking at this region that's bounded by the two curves. So we're going from one intersection point to another. And what those intersection points do is they give us an interval, a section of the x-axis to consider. So our interval here is from -1 to +1. And again, we're just looking at a section of the x-axis. And what we want to know is, on that section, which of our two functions is higher up? That's all we're trying to figure out. And so if we look at our graph, one of the curves here is a parabola. The other curve here is a line. And if we go to our two functions, the parabola is the function with the x squared, and then the line is just the function that just has the power of x raised to the power 1. So we can see here, on just this section of the x-axis, it's the line that's higher up on the page. So we can say then that our top function is y equals 2x plus 4. And our bottom function, the one that's lower down, is the parabola. So we just have to identify this just to help us set up our integral. All right, so we can just kind of tell this from looking at the graph. If we didn't have the graph, though, how could we do this? Well, we still want to check on this interval from -1 to +1, and what we want to know is which function is higher up, which one has the bigger height. So we can use a test number. If we want to confirm this, we can use a test number and then plug it into both of these functions and see which one gives you the bigger value. So in this case, again, we're only looking in between -1 and +1 here. So we could pick any number as long as it's inside that interval. So 0 is always nice. And the idea here with a test number is we're just going to plug this into both functions. So we're going to plug it into our y equals 2x plus 4 function. And when we do that, we get y equals 2 times 0, which is 0, plus 4. So we get y equals 4. Help if you could see. And then when we plug it into the other function, y equals x squared plus 2x plus 3, well, we're going to get a 0 here, a 0 here, and then plus 3. So we're going to get y equals 3. And all we're doing is we're just trying to identify which of those values is bigger. And so in our case, y equals 4 is bigger. So that's what's telling us that the top function is 2x plus 4. And the y equals 3 value is, well, it's a little bit smaller. So it's lower on the page. So really that's why we're going to choose the parabola there as the bottom function. So when we're ready, now we have all the information that we need to actually set up the integral. So the area that we're trying to do is going to be the integral from -1 to +1. Again, we're looking at that interval. We only have 2 intersection points. And then we want the top function to come first. So we're going to put the top function here. And then we're going to subtract. And then we're going to have our lower function, our bottom function. And that's going to be second. And when you do this, when you set up the integral, good idea to throw some parentheses around everything because we have this subtraction. All right, so let's fill in our functions. We're going to throw in a 2x plus 4 here. And then we'll throw our x squared plus 2x plus 3 right over here. And at this point, we want to simplify it down. So we have the integral set up, but now we want to simplify this down, this function down, as much as we can. So try to do as much of the subtraction as possible. So in our case, we have a 2x minus a 2x. So those are going to completely cancel out. Then we have a 4 minus a 3. So that's going to leave us with just a 1. And then we have minus x squared. So we'll have a 1 minus x squared ultimately for our function. And we're going from -1 to +1 still. So it is helpful to simplify the function as much as you can because Here we only have two values, two pieces to integrate, which will just make everything then easier when we get to the evaluation part. Whereas back here we have 5 things to integrate. So you do want to try to simplify the function down as much as possible, just to save on some of the steps that follow. All right, so let's get the antiderivative. Antiderivative of 1 is x. Antiderivative of the negative x squared is negative 1/3 x cubed. And then we're going to evaluate this from -1 to +1. And then when we do our evaluation for definite integrals, again, it's helpful. Get some nice parentheses set up. And then what goes into the first one is what we get when we plug the top number in to our antiderivative. And then what goes in the second one is what we get when we plug the lower bound in. And let's see. So top number is going to go in. We get 1 and then -1/3. And then when I plug -1 in, I'm going to end up with a -1 and then -1/3 times -1 cubed. And, we could simplify this down. It's just powers of 1 and some negatives here to keep track of. So this actually does simplify. So the one thing here just to keep in mind is that -1 cubed is -1. So this is actually going to become +1/3. And if we so if we do that, we're going to have -1 +1/3. And then distributing the negative, we end up with, and combining like terms, we're going to end up with, 1 minus a -1, so 2. And then -1/3 minus a +1/3 is going to be -2/3. And then, we could go a little further, get a common denominator, and we end up with 4/3 here as our answer. And the nice thing about getting it down to one number is this tells you, kind of gives you an indication if you did things right or not. So this value should be positive. So just a little note. Oops. Area should be positive. So if you're doing it and you get a negative value there, chances are you want to go back and check something, but 2 places where you might have just mixed things up, double check that you chose the correct top function, and then also double check that you evaluated in the correct order. And that's it. So that's the idea with finding the area bounded in between 2 functions. And I was going to say one other thing here. Yeah, when you get this simplified version of your function, this 1 minus x squared, it should look similar to this equation that we got when we were finding the intersection points. It might be, the negatives might be switched around based on how we solve the equation, but it should look similar. So going back, we ended up with this x squared minus 1, and once we simplified the function, we ended up with 1 minus x squared. So very similar looking, just the signs are opposite. So that's okay. So that's another way to kind of just check if are you simplifying correctly as you go. If you simplify the function, it should look similar to what you had before. All right, so we're going to try, another example like this in class. So we'll get a little bit more practice in. That's a fun one. All right, so we'll see you then. Bye-bye.